Hello and welcome. We're going to be working through question 1 from ACE Physics paper 4. This comes from 2017, October-November administration, paper 42. All right, state Newton's law of gravitation. That's relevant physics. Newton's law of gravitation says that the force of gravity is directly proportional to the product of the masses, right? So we have sort of mass 1, mass 2, separated by a distance r, and Newton's law of gravitation describes how strong gravity is between sort of two massive objects that are separated by a distance r. And Newton realized that the force of gravity is directly proportional to the product of the masses. That is to say, the more massive the objects are, the more gravity there is going to be between them. We can sort of write this, the force of gravity is directly proportional to the product of the masses, all right? And inversely proportional to the separation distance. Separation squared. So it's an inverse square law. So it's inversely proportional. So in the denominator down here, the distance, which we're calling r, squared. So this is the physics here that describes sort of how strong gravity is. It's related to two things: how massive the objects are that are interacting and how far apart they are. And it goes sort of, gravity gets weaker as the square of that separation distance. So if I were to separate these things twice as far apart, gravity would be 4 times weaker. If I put them 3 times further apart, then 3 squared is 9, right? So gravity is 9 times weaker. We'd be dividing it by 9. If I double the mass of something, if I have a star that's twice as massive, right, then gravity is twice as strong, right? Because it's just directly proportional to that. To turn a proportionality into an equation, you need a constant of proportionality. And so there's an experiment conducted in 1802 by Henry Cavendish, where he first discovered or determined Newton's universal gravitational constant. So this is the law of universal gravitation, and this constant right here, G, sort of turns this proportionality, this law of physics, into an equation. And this is the equation that we're going to sort of employ here for the remaining part of the paper. All right, so that sort of describes it in words. This describes it sort of mathematically. You could have sort of answered this by just sort of writing this equation out, but also defining each one of these variables, right? You say, the force of gravity is equal to gmm over r squared, where m is the mass, r is the separation distance, g is the universal gravitational constant. For completion's sake, let me give you the value of that. G equals 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Those are the units of it. For everybody following along at home, you can pause the video right now, get that written down. All right, let's continue. It says the planet Jupiter and one of its moons, Io, may be considered to be uniform spheres that are isolated in space. Jupiter has radius capital R and mean density rho. Io has mass lowercase m and is in a circular orbit about Jupiter with radius nr, as illustrated in figure 1.1. So if you think about that, they're telling you that the planet itself has a radius r, and they're describing how far away the moon is a number of those Jupiter radii away, right? So Jupiter has a radius that's r here, and they're saying, well, there's so many, Jupiter radii away to get to the planet Io, right? So n is just a number, how many times you would multiply Jupiter's radius by to get out to Io's orbit. So you're just gonna say, okay, Io is one of those planets. The sun might be over here, and Io might cast a shadow on the planet Jupiter, just like we saw. Let's show everybody the APOD from today. So today is October 7th, 2022. And this was today's APOD and the inspiration for this pop quiz that you get to answer right now. Lucky. The time for Io to complete one orbit of Jupiter is capital T. And we're just going to show that the time T is related to the mean density rho of Jupiter by this expression. Rho T squared equals 3 pi n cubed over G, where G is the gravitational constant that we mentioned earlier. All right, we should be able to make short work of this. No trouble at all, right? No problem. 4 marks for that. So today's the last day of the grading period, and this is worth like, I forget how much I thought. It's like 1,000 points or something like that. So it's going to make or break your grade, unfortunately. So go ahead, it's due, and I'll give you, I don't know, 5 minutes. Just kidding, right? That would be disastrous. Let's think through it together, though. We should be able to do this. All right, we know some things here. They gave us a lot of clues. Let's read the clues. T, so that's the time. I mean, just think about how awesome this is first. We're going to be able to relate the time that it takes the planet, the moon to orbit to the density of Jupiter. Like, how dense is this planet? You know, how much stuff fits inside of it, and that's sort of related how long it's going to take and how far away it is. That's this number n. Remember, we said n is like how many of Jupiter's radii do we need to go out to sort of get to that. So I think a big clue here is going to be this circular orbit. Okay, circular orbit. All right, so let's keep that one up there. Remember, what we're trying to get to is that. And here's the ideas we need. In order for something to move in a circle, there must be a centripetal force, okay, a centripetal force. That's always equal to the mass of the thing orbiting times its velocity squared over how far away it is. But remember, how far away Io is n times r, right? It's the number of Jupiter radii away. So this was the distance that they gave us. If you didn't already sketch this figure in your journal where you're doing your working, I would do that now. In fact, I might just want to do my working up here. Let's do that. All right, so in general, for anything to move in a circle, there has to be a force that acts on it that's equal to this, mv squared over r, where r is how far away it is. You can see that Io, they assigned it as lowercase m. So we have Io's mass times its velocity, and that's its velocity sort of this way. Okay, so we'll have to sort of think about that too. What is providing the centripetal force? Centripetal means center seeking. So there's always a force that's acting towards the center of the circle. You can imagine that the force that's acting towards the center of the circle here is gravity. It's sort of provided by gravity. And so we have a rule for that, the force of gravity, Gmm over r squared. So we know that gravity, which is equal to this, is providing the centripetal force, which is equal to this. And so we can set these equal to each other. Gmm over. Now this is how far apart they are. So once again, in general, it's r squared, but how far apart is Jupiter from Io is this value, nr. And so that's what we actually have to square down here. So it's going to get worse before it gets better, you guys. I mean, look what we're trying to get to down here. Rho t squared equals 3 pi. Like, where's the pi coming from? Like n. Some things are going to have to cancel out here. This is not going to be good. One of the things that I can anticipate is that the mass, capital M, that's the mass of Jupiter. But that's not anywhere in this equation down here. So we have to express it in terms of density. Density, the density of this planet is its mass, m, right? Capital M is Jupiter, over its volume, okay? Density is mass per volume. Remember, they said we're assuming these are uniform spheres. Everybody out there knows that the volume of a sphere is, that's right, 4/3 pi r cubed. And here r really is the radius of Jupiter. So once again, capital R is how big is the planet? And then we say, well, Jupiter is how many times out do we need to go to get to Io, right? How many times of that radius? That's nr. So we're going to express the mass in terms of this, right? Let's rewrite this slightly. The mass of planet Jupiter, capital M, I'm multiplying both sides by this denominator. So it's going to be equal to rho, then I multiply it by, let's put the 4/3 out here, 4/3 pi r cubed. So that's what capital M is. You can, again, anticipate we're going to have to substitute this term in for M over here. All right, so let's see what this is going to look like. mv squared over nr equal to this g. Now, I'm not going to substitute this yet. Okay, let's just clean it up a little bit first. Remember what this squared means. It's nr times nr. Anytime you see the same term in the same place on either side of an equation, you can cancel it out, right? So this is like nr squared. That's like saying nr times nr. Well, one of those is going to cancel. So you just have nr left on this side. Also, the mass of IO itself doesn't matter, right? We could divide both sides by lowercase m and realize that that's going to cancel out. So it does simplify a little bit. We got v squared equal to g m over n times capital R, where R, again, is the radius of the planet. Now it's better to sort of make that substitution. Also note that v, the velocity, which is like the sideways velocity of the planet, how fast it's going this way, that is not in our final equation. So we have to think about how we could substitute for that. This gets back to the idea of this is circular orbit, okay? The velocity all right, I had to puzzle through that one a bit, but if you think about circular orbit, it's 2 pi. Now, r here is going to be nr, right? So it's the circumference of this circle, right, which has radius nr. So circumference is 2 pi r. That's the distance traveled, and the time that they tell us right here is t, right? The time for IO to orbit is t. So we can just sort of use the definition of velocity, like distance divided by time, but the distance is the distance around a circle. And it's kind of nice because here we've introduced pi, and there is a pi in our final answer. So it's like pi's got to come from somewhere. And again, the clue in the question was the word circle, right? It's circular orbit. And you've learned before how to calculate circumference. It's just a little bit unfamiliar because the radius is in terms of this nr, right? So we're going to have to substitute this guy in for v, and we have to substitute all of this in for m. And hopefully by the time we're done, it looks like this thing down here. Okay, rho t squared. So if you're good with that and you're like, okay, it's like a little puzzle and I've got all the pieces, let me kind of put them together now myself, go ahead and get a head start, okay? If you're following along at home, go ahead and pause the video, try it for yourself and see if you can't come up with that expression right down there. Rho t squared equals 3 pi n cubed over g. We got all the ingredients, right? There's g, there's pi, there's t. Don't forget to square every term in this, right? V here is squared. So that's why it's going to get worse before it gets better. I'm going to rewrite it up here. V squared equal to g m over n r. I'll sort of rewrite this over here. V equals 2 pi n r over t, and m equals, that's this one right here, 4/3 rho pi r cubed. All right, so we got clean that up over here. So that's where that came. All right, so here we go. Plugging in v first. So v is 2 pi n r over t, but everything that, you know, is here is squared, right? V is squared. So, well, 2 squared is 4. That's not too bad. Pi squared, n squared, r squared over t squared. Everything has to be squared on the left side because v is squared. And then on the right side, we have g. Now, m here is this, you know, capital M. It's the mass of Jupiter. And so it's going to be 4. Now I'm going to put the 3 down here since there's terms in the denominator. I'm just going to do 4/3 like this. So 4/3, the rho is up here, the pi is up here, and r is cubed up here. Okay. And then I still have this n r down here. Right away, I could see that this one of these r's is going to cancel this r, right? So that's really r squared. And then when you have r squared, again, on both sides of the equal sign in the numerator, we could divide both sides by r squared, right? Effectively canceling r. Note how r isn't in our final expression, right? So that's nice. We've just canceled it out. We've just shown that, yep, it goes away, cancels out. One of these pi's is going to cancel. It's always a shame to cancel pi, you guys, but oh well. We still have one left, right? There's a pi still left over on this side because we could, again, just divide each side by pi. Pi divided by pi is 1. 1 times the rest is the rest. So then what are we left with on this side? One of these pi's, the 4, right? 4 pi n squared, it looks like, over t squared is left on that side. And over here we got g, 4/3, got the row over there. We got an n down here. I think that's it. But then if we multiply both sides by n, then this n squared times n is n cubed, right? So that sort of gets rid of that on this side. Now there's n cubed, and that's the way it should look. Let's see, we're trying to get rho t squared on the same side. So there's rho, let's multiply both sides by t squared, right? T squared. So that sort of achieves what we want on this side, but we got to get rid of this divide each side by g, divide each side by 4. So divide each side by g, divide each side by 4. And then we got to multiply both sides by 3, right? So 3 times 3 is 1, so you got to multiply this side by 3. All right, so these g's cancel, these 4's cancel. I'm left on this side with rho t squared, what I wanted, to have those terms together. And then on this side, the 4's cancel. I have a 3 right there. I got a pi. I've got an n cubed, and all over g, right? So I think, indeed, that agrees with what we should have got, what they said that we should get. So we've just shown that the density of the planet is related to the time that it takes its moon to orbit, right? Because you multiply those two together on the left side, and it's equal to just, some constants. 3 and pi and g are just numbers, right? Like we could just turn that into a single number, but it's related to how far away it is cubed. This is really a restatement of something that Johannes Kepler realized, in the 1500s or 1600s, his third law of planetary motion, that the orbital period squared is related to how far away it is cubed. It's true for planets around the sun, and it's true for moons around planets, anything that orbits. And so we've just kind of shown that here 5 centuries later. But the Newton way, okay? So, Kepler really never knew the values of these constants, but he did figure out the sort of the proportionality like we talked about earlier. All right, it looks like we get some numbers here to work with. So let's keep a good thing going. Raise your hand if you needed any of that working, or just leave it down in the comments below. Say, that was pretty good working. All right, go ahead and pause the video. All right, so it looks like they give us the radius of Jupiter, the distance between the centers, the period is 42.5 hours, and we have to calculate the density of Jupiter. That's what they want us to do. All right, easy come, easy go. Get rid of all that. But let's remind us remind ourselves what it was. It was rho t squared equals, what was it? 3 pi n cubed over g, right? I think that was it. And so they say calculate the mean density of Jupiter. So we're calculating the density. So let's just divide t squared right off the bat, right? So now density is all by itself. That's what we're calculating. And we just need to plug in everything. Oh, wait, we don't know n. So the radius of the planet r is given. That's how big Jupiter is in kilometers. And I remember, was out here, and they're saying the distance between the centers is 4.32 by 10 to the 5th. The radius is 10 to the 4. So we have to just divide these two into each other, right? We're calculating how many of these r's. Is it 2 r's, 3 r's, 4 r's, 5 r's? How many times do we need to multiply Jupiter's radius by? How many times do we need to multiply this number by to get this number? Or rather, what is this number divided by that number? Can anybody do that in their head? Sounds like I'm typing buttons in a calculator. That's just an artifact of the technology. I'm actually doing some mental math right now. everybody in the lab can look back and see that that's not true, but YouTube doesn't know. All right, so I just crunched those numbers really quickly in my head, and I'm getting around 6, but I think if I actually carry it out to the 100 millionths place, it's like 6.0419588042, something like that, maybe. But it's about 6, right? So let's just say n, it takes 6 of these Jupiter radii, right, to get out to Io. In other words, if you multiply this number by 6, it's about that. It's like 6.04195, thereabouts. All right, so good. We got n. I think we know what pi is, right? We know g. Oh, t, look, they give us t in hours. That's no good. When we plug in g, the units that I mentioned earlier, Newton meters squared per kilogram squared, there's actually another way to write this. This is per kilogram squared. Students of physics will know that a Newton is a kilogram meter per second squared, right? Those are the base units of the Newton. So if we plug that in here, we'd have what? Kilogram meters per second squared. That's the Newton. Then we have these other meters squared, so it's meters cubed, and then these per kilograms down here. So we can see that that kilogram is going to cancel one of those kilograms. And see how you have meters cubed per second squared, and this relationship relates the time squared to the distance cubed. So you see that sort of within the units of g, right? Distance cubed and time squared. We're restricted to the units of seconds because of that. Because a Newton is a kilogram meter per second squared, we have to convert this into seconds. And so hours to seconds, we're going to multiply that by 3,600 seconds per hour. So to get the time correct, to plug in the correct value for time, we have to multiply 42.5 by 3,600 seconds per hour. So 42. So how many seconds is 42.5 hours? It is 153,000 seconds I'm getting. All right, I think we got it all now. Ready to go? The density rho equal to 3 times pi times 6 cubed over, right, because remember n is 6. We calculate that over here by dividing those. G is 6.67 by 10 to the negative 11. Now let's use the units here. Newton meters squared, all right. Oh no, sorry, it's Newton meters squared per kilogram squared. So those are the units of G. Let me clean that up a bit. Sorry, everybody. Newton meters squared per kilogram squared. Those are the units of G. These don't have units, right? They're just numbers, right? In other words, these kilometers cancel it out when we divided to get this. And then the time down here is 153,000, and it's squared. And so it's in seconds, so those are squared. So the Newton here is, remember, a kilogram meter per second squared. So the seconds squared are going to cancel. The 1 kilogram is going to cancel. We're going to be kilograms per meter cubed, right? Those are the units. So see how it sort of checks out? That's kind of nice. All right, 3 times pi times 6 times 6 times 6 divided by 6.67 by 10 raised to the negative 11 divided by 153. All right, I'm getting 1,300, about 1,300 kilograms per cubic meters. Hey, everybody, have a good weekend. Go Commodores. All right, YouTube, let's keep on going with this calculation here. The end of the period, it's Friday, so early release, so class gets done a few minutes early, but we won't let that stop us. The last part of this just says that the Earth has a mean density of 5.5 by 10 to the 3, and it's said it's a planet made of rock. You know, that's what it is said about planet Earth. By reference to our answer, comment on the possible composition of Jupiter. Well, because our answer is like way less, 1303, we might conclude that it's composed of something less dense than rock, like gas. Maybe Jupiter is a gas giant. You've heard it here first, YouTube. This is Dr. Schleif, still living the physics life. We'll see you next time.